When we look at reactions, they don't always have one reactant. Single replacement, double replacement, combustion reactions all have more than one reactant. So we come across this problem of a limiting reactant issue. A limiting reactant or reagent is completely consumed by the reaction, so it runs out. Excess reagent or reactant is not completely consumed, so you have leftover of the excess reactant, but the limiting reactant is completely consumed. So if we think about making grilled cheese sandwiches, we need 2 pieces of bread, 1 piece of cheese to make 1 grilled cheese sandwich. But if you go to your kitchen and you have 6 slices of bread and 2 pieces of cheese, then you are limited to 2 grilled cheese sandwiches because of the cheese. The cheese will run out first, meaning that that is the limiting reactant. I tend to abbreviate limiting reactant as LR, leaving the bread as excess reactant or ER. So we would use 2 slices of bread for every 1 cheese. And what we see is that we'll make 2 sandwiches and have 2 pieces of bread left over. So to solve these problems mathematically, we take both of the givens that are with reactants and convert them to moles. Then look at the ratio using the coefficients to determine which one will run out first. Finally, use that limiting reactant to figure out how much of the product is going to be formed. So we're going to look at 4 examples. We have our balanced reaction. If we list what we're given underneath, 2 moles of HF, 4.5 moles of silicon dioxide, and it's asking for liters of water. So notice in these problems we have 2 amounts given to us and 1 thing that we're trying to find. Both of the amounts given are with reactants, so it's a limiting reactant problem. The first thing we would do is convert our givens to moles, which they already are. So then in our head, what we want to do is determine which one we'll run out of. So you take the moles and you divide it by their coefficients. So 2 divided by 4, 4.5 divided by 1. That will determine which one would run out first. So whichever is the smallest is the limiting reactant. Well, 2 divided by 4 is going to be smaller than 4.5 divided by 1. So HF is your limiting reactant and silicon dioxide would be your excess reactant. So then to solve the actual problem of the volume of water produced, you would start with your limiting reactant and go through the steps of stoichiometry. Turn your given into moles, already done for us. Then use the mole ratio to go from your given to what you're looking for. Remember the mole ratio, you use your coefficients from the balanced reaction, so 4 HF and 2 H2O. Then we want to go to the units that the question is asking us for, which is liters. So we would bring down moles of water and put liters of water on the top. And then based on our roadmap, 1 mole is 22.4 liters. So when we multiply and divide, moles of HF cancel, multiply and divide, moles of water cancel, leaving us with the volume of water. And so our answer with 2 significant figures is 22 liters of water. Let's look at a harder problem. We have 20.5 grams of chlorine and 20.5 grams of sodium. They want us to determine the theoretical yield in grams of the product. So we're looking for grams of NaCl. So we have 2 givens that are both reactants, so it's a limiting reactant problem. First thing we need to do is convert from grams of chlorine to moles of chlorine, and then grams of sodium to moles of sodium. So we would put grams on the bottom, mole on the top. Based on our roadmap, 1 goes with mole, and then the molar mass of chlorine There are 2 chlorines though, so 35.45 times 2 is 70.9. When we multiply and divide, the grams would cancel, giving us 0.289 moles of chlorine. Now we're going to do the same thing for the sodium. 20.5 grams of sodium, grams on the bottom, moles on the top. 1 mole, and then on the periodic table, sodium is 22.99. Multiply and divide, your grams would cancel, giving us 0.892 moles of sodium. Once you have your given in moles, then you divide by the coefficients. So we would divide by 1, we would divide by 2. Dividing by the coefficients, chlorine is still the lowest amount. So this is still going to be our limiting reactant, and sodium is our excess reactant. So to determine the mass of our product, we're going to want to use grams of chlorine. We want to use our limiting reactant. Well, the first step to stoichiometry is to convert your given to moles. So we've already done that. We're just going to pick up here. So we have moles of chlorine. Step 2 to stoichiometry is using that mole ratio to go from chlorine to sodium chloride. Use their coefficients 2 and 1. Then we want to go to grams. So we would pull moles of sodium chloride to the bottom, grams of sodium chloride on the top. 1 mole, and then sodium plus chlorine is 58.44 grams. Multiply and divide across will cancel out your moles, leaving you with grams of sodium chloride. So the answer then would be 33.8 grams. Here we have methanol, and we're combining carbon monoxide and hydrogen. So we have 14 grams of carbon monoxide, 1.51 grams of hydrogen. We want to know how many moles of methanol are formed. Limiting reactant problem, because you have mass of both reactants. First thing we want to do is convert that to moles so that we can compare them. So grams on the bottom, moles on the top, 1 mole, and then carbon plus oxygen is 28.01. That gives us 0.500 moles. I rounded it so it was 3 significant figures. Then we have 1.51 grams of hydrogen. Hydrogen's molar mass is 2.016, because there's 2 hydrogens. And that is 1 mole. And so we would get 0.749 moles. Then we need to divide by the coefficient. So we would say divided by 1, divided by 2. So that would mean our hydrogen is our limiting reactant, because when we divide 0.749 by 2, we get 0.37, which is smaller than 0.5. So this is my limiting reactant. This is going to be my excess reactant. And then we just have to do the stoichiometry to get to moles of methanol. So we always start with our limiting reactant, 1.51 grams of hydrogen. We've already converted it to moles of hydrogen, so we're going to pick up there and go to our mole ratio. Moles of hydrogen to moles of methanol, using the coefficients 1 and 2. And since we're looking for moles of methanol, we can stop there. We don't need to do that third step. So when we multiply and divide, the moles will cancel, leaving us with 0.375 moles of methanol. One more. We have 100 grams of sodium and 100 grams of iron 3 oxide. We want to know the limiting reactant and then the mass of iron produced. So again, 2 givens with the reactants. We need to take those and convert them to moles so that we can compare them. So we're going to take the molar mass off the periodic table, and that is 1 mole. For the iron 3 oxide, for the molar mass, we would add 2 irons and 3 oxygens to get 159.7, and that's for 1 mole. And that would give us 0.6262 moles. So again, we're going to divide by the coefficient. So 4 divided by 6, and then 0.6 divided by 1. When we divide this, that would give us 0.7. This is 0.6. So iron 3 oxide is our excess reactant, and sodium is our iron 3 oxide is our limiting reactant, and sodium is our excess. So we're going to use that limiting reactant to then find the mass of our product. Take our grams, convert it to moles. That's always step 1 to stoichiometry. So the next thing that we're going to do is set up our mole ratio. So moles of our limiting on the bottom, moles of the product we're looking at on the top, using their coefficients 1 and 2. Then we want grams, so we're going to do one more step and go from moles of iron to grams of iron. Based on our roadmap, 1 mole is equal to the molar mass of iron from the periodic table. Multiply and divide. Moles would cancel, leaving us with grams of iron. So the answer is 69.95 grams of iron.